Okay. I'm Ruben, as Dragon said, and you already said my Slack name. So I am studying a Bachelor of IT. I'm currently in my second year. So I have a talk. It's on writing performant code, and I have slides as well. But it's not the high-level stuff like how to write efficient map-reduce queries or how to properly architecture code. This is more about the low-level stuff and the mindset behind how to write performant code. Okay, so writing performant code. That's just my info. I've been programming for 4 years now in my spare time. Okay, so this talk. This is more about how to think about coding when you want to write high-performance code. Not in the sense that you want to go write code that'll map over millions of queries and has to take really fast, because that's an entirely different set of problems, and that's a very specific way you have to think. But this is more about, in general, you can apply this to any type of code you write, and your code will probably be faster. So I have 3 areas, or 3 sections. The first is know your hardware. So I had a few more dot points here, but I cut them because lightning talks. So the CPU cache is the part I'll be talking about when I talk about know your hardware. So this is the basic data pipeline in a modern computer. At the top you have the CPU registers, and at the bottom you have the input sources. And since it's in a nice little pyramid, you can guess that at the top is the fastest and the bottom is lowest. So the parts I'm going to be focusing on are the cache and the RAM parts. So this is a modern i7 processor, and you can ignore the top and bottom parts and only focus on the 6 cores and the L3 cache. So how this works is your computer has the big RAM, which has a lot of memory and a lot of space to store things in. And then, but the RAM's slow because it's so big. The bigger you get, the slower things tend to get. So what CPU manufacturers did in about the 1980s is they started adding caches and stuff. So the L3 cache, you can see, is shared by all 6 cores, which means all 6 cores basically tap into that. And then each core also has an L2 and an L1 cache. So the L1 cache is the smallest, but also the fastest. L2 cache slightly bigger. L3 cache is way bigger than all of them. So this is a piece of C code, and you'll be glad to know it's in Vim. And so this is to basically explain how the cache works. So all I'm doing is making an array of 5 integers, looping over it, and printing each of it. So if we assume that between the int array 5 part and the for loop, a bunch of stuff has happened, and this isn't in local memory anymore, in the cache that is, what will happen is the CPU will say, okay, I need the first value of the array. And then it'll say, okay, I'll check the L1 cache, and then if it's not there, the L2 cache, L3 cache, and then the memory. And so it'll go all the way to memory, get the first value, but because the buses in modern processors are bigger than just 8 bits, or a few bytes or whatever, it'll grab a couple of values afterwards as well. So in fact, when I get the first value of the array, it'll grab a few values afterwards as well and chuck that into the cache as well. So what happens is the first access of the value will be pretty slow comparatively, and then the rest will be blazingly fast because the values will already be in the cache. So how much slower? Well, this is how it'll look in memory, basically, the array. And the first address up to the 4th address all contain 0. And so this is the speeds. So to get something from L1 cache, it's about 0.5 nanoseconds. L2 cache is about 7 nanoseconds, and from RAM it's about 100 nanoseconds. So this is average for about a desktop platform. And these aren't very big values, but they do add up immensely over time. So if you're doing something like a game, we're iterating over 10,000 entities, and you have to get it from cache every time, or from RAM every time rather, it's going to add 200 times the performance penalty that you would have if things were more sequential in memory. So Benchmarks. This is a C function, or a C++ function rather. It makes, I think that's 10 million. It makes a vector of 10 million integers and also a list of 10 million integers. So how a vector works is everything is laid out next to each other in memory, like an array. How the list works, which is a linked list, the first value stores a pointer to the next value, which stores a pointer to the next value, and so on and so on and so on. And so what I did was I just basically sorted each one 5 times. Why 5 times? Well, I wanted a value, time that's in the seconds, and I ran out of memory, just increasing number. So these are the values I got. The vector sorts took about a second rather, and the list sort took about 4.8 seconds. So this is on MSVC 2015 compiler release mode, and they both use Quicksort, so it's not the sorting function. This is all about cache, and that's because the vector has a way easier time of loading everything in cache because it's all next to each other, whereas the list, if the next value isn't next to the first value, it has to basically go back to memory and get it, which incurs a pretty big penalty over time. So the second section I have is know your language. Now, knowing your language also has a subsection, know your abstractions. So there are a few parts of the language which are really important to know. Things like the memory model, for example. How does your program handle memory? Is it garbage collected? Does it store things on the stack? Java, for example, stores primitives, so basic integers and stuff, on the stack. It stores every class or every non-primitive object on the heap, which means for every time you make an object, that's an allocation that you have to do. Things like the standard library. What are the different performance penalties of standard library things? So if you're using C++, for example, know when to use a vector or when to use a linked list, for example. Chances are you don't want to use a linked list. Java as well, array list versus vector in the Java standard library. What's the difference? They're basically the same, except vector has concurrency synchronization. So if you're writing a concurrent program that you want to all access the same data structure, you might want a vector, but an array list will get you a lot of speed ups if you're not writing that. So also a bunch of high-level constructs. So if you're using C# and you use link, that's very slow in the grand scheme of things compared to a for loop, for example. It has to allocate a bunch of iterator objects. It has to do a bunch of stuff to map over them, stuff like that. Also runtime. So a good example of this is Go. Go has a runtime that manages all the Go threads and manages the segmented stacks and stuff. And the problem with that is when you call a C function from Go, it has to basically suspend all the threads, create a default C stack, keep all the other stacks away, and that incurs a massive penalty. So calling a C function from Go, for example, is about 20 to 40 times slower than calling a Go function. So Python is an example. Python's interpreted, and that in itself means you can make a lot of assumptions about how it works. So if you had a C loop, a for loop in C, and you called a function in it, you could be, and it's not one of those functions that changes or that is the same every time in the loop, so you want it inside of the loop. A C function will basically point to its place address in memory, which means it won't be as slow. There will still be function overhead, but it won't be as bad. A Python function stores the function in a global hash map. And every time it gets to that point where it needs to call the function, it needs to go check into that hash map and then get back to it. And so when you're writing a Python program and you have a very hot for loop, chances are you might want to store that function in a local variable because local variables are fast to access. Things like that make a big difference in a very high performance spot. Also things like for loops versus maps versus list comprehensions. You can think of a map as basically just a for loop is extracted into C code, and a list comprehension as a highly optimized, highly specific form of a map. So this is basically know what your language does when you do a certain thing. If you look at a C, it gets harder, but if you look at C, for example, you can basically make a reasonable assumption about what will happen on the physical machine when you do this. And one of the things about writing performant code is know that you're writing for a computer and take that into account, because a lot of code is written with these very heavy abstractions and mental models, and they're very divorced from how a computer actually works. A computer has a CPU and RAM, and there's a lot of things that if you take them into account, your program will run better on a computer because you're writing it for a computer. So I also had Go. Go does, so I mentioned the C call overhead, but things like the stack and the heap on Go. Go tries to allocate as much on the stack as possible, and the stack's faster to access memory from than the heap. The way it does this is it does a thing called escape analysis. So escape analysis is where if you take a pointer to an object, it tries to see if the pointer escapes outside of the function scope. If it escapes outside the function scope, it knows this object has to go on the heap. This is also, if you use GCC Go, which is a different Go compiler which uses GCC, doesn't have escape analysis for Go as of yet. And that means that all your objects in Go get allocated on a heap instead of a stack if you use GCC Go. So things that you have to take into account as well are different compilers. And this gets very hard to do if you use something like C or C++, where there's 3 major compilers and all of them have weird ways of doing things. But it's important to take into account what your program does. So this is my third section. The fastest code is the code that never runs. So I have 2 dot points, data structures and algorithms. So for data structures are a great way to minimize the amount of stuff you have to do, or save memory, or make things fit more efficiently into memory. So vectors and arrays are a great way of making things fit better into memory than, say, a linked list. So here's an example, collision detection. If you have something like a game or something that represents objects geometrically and moves them around, and you want to check collision, the most naive algorithm or way of doing it is to basically put everything in one big array and just loop over everything twice, and then you get a quadratic loop where you're just comparing every object to every object. And this is fine if you have a really small amount of entities, but once you get to a really big game, like if Assassin's Creed did this, it would run even worse than it does. So, so the solution to that is to use a tree. So this is a tree, a data structure tree, and so what a tree basically is it has a master node, which then contains a certain number of objects, and it points to either 0 or X separate nodes. So this is a binary tree. It can point to either 0 or 2 nodes. The bottom tree nodes point to 0 nodes, and the top to 2. Okay, so what a tree does is it's used to sort data in an efficient manner. So you'd use a binary tree, for example, if you want to store objects that have one value associated with them, and you want to find them really fast with a equals or less than, for example, sort. So this is what you'd use for a geometric algorithm. This is a quadtree, and what it does is it basically takes a square, which is the square that your objects are in, and it starts inserting objects into that square. And once you get to a certain max objects, you basically divide the square into 4 smaller squares that each fit into in a quadrant. And you basically just insert the objects into the squares that they match in. And you keep doing that until you have the basically the right amount of objects in each square. And so if I want to, say, take a dot anywhere and say what collides with this object, all I have to do is basically just follow the squares, which means the amount of objects I'm actually comparing with is just the amount of objects in a square. For example, if we go back to here, if the first value, the first node has, say, a splitting value of 5, for example, and I want to find a value that's less than 5, I just have to go to the left half of the tree. And then if that value contains a 4 and I want to find a 3, then I just have to go to the left again. And so you can see the basic. I'm basically sectioning off an entire half of the tree that I don't even need to think about, because I can find a path straight through the tree. So now we have algorithms. So Quicksort is a sorting algorithm, and any person who's ever looked at Haskell will probably know Quicksort very well. So what Quicksort does is it's a recursive algorithm. You take a collection of elements that can be sorted. You take the first element, and then you go through the collection. Find all the elements that are less than it, and find all the elements that are greater than it. You put the elements that are less than it on the left of it, and then do the quicksort on that, and you take the elements that are greater than it, put it on the right, and do a quicksort on that, and eventually you'll end up with basically a sorted list or collection. And this is really fast compared to a more naive sorting algorithm like bubble sort, for example. So I have a nice video of it, and I think I'm connected to the internet, so it should load with nice sound as well. So here we can see it's comparing on values, and it put the middle value there as the green one, and then it's comparing all the values to the left and to the right of it. And so that's basically how it works. So my second algorithm is to find a string in a string. So let's assume you have a really big code base, like at Oracle, and one of your developers is dyslexic, and instead of typing int64, they type int46. And so you are tasked with having to go in, find all of these, and replace them. So this is a world where fancy IDEs and SED and stuff don't exist. So you basically have to go write a program to do this for you. Now, the naive approach would be on the left. You basically compare the first element of your substring with the big string, you move along. If you get a match, you just compare the second element with the element after that. So this is something you'd write in CSSE 1001, and it'll work and no one will complain. But when you get to really fast code that you need to execute, you need a better algorithm. So what GNU grep does is it uses the Boyer-Moore algorithm. And that basically, before it starts searching, it creates a jump table. It says how far is a character away from the character on the right. And if the character isn't in the substring, it just says it's the length of the substring long. So what we then do is we compare the rightmost character with a character in the bigger string, and we check the jump table. We check if it matches that character, and then we check in the jump table how far along we'd have to jump if it doesn't match. And so what we end up with is basically what you can see here. So it starts with an H, then it says, okay, the O isn't in my jump table, so I move 4 along. Then we get to the T, and it says the T is in my jump table and it's 1, so we move 1 along. And this is an excessively fast algorithm compared to the more naive approach. So the basics here is you have sort of 2 sections, I guess, in the talk, if you take the 3 sections and make them into 2. The first one is know what you're doing, or know what things are doing for you. So know what your programming languages are doing for you. It doesn't mean you have to go and check the assembly output of your code every time before you run it, but at least have an idea of what the code does when you execute it. So if you have a simple program in any language and you press go, what does it do? And not just what does it do in the logical sense, but what does it do in the computer sense? Where do you expect memory to be allocated? Where do you expect CPU to happen? Stuff like that. So I have a few further reading options. So Programming Pearls is a really good book. It's one of the top 100 programmer books. It goes into a lot of these things. It explains how to. The first chapter is on bit sets, and if you don't really think in a way like this, it might completely blow your mind. There's also game programming patterns, which tries to be more generic than that. It tries to give you a bunch of patterns that you might use in games, but it doesn't just give you them, it gives you justification for them. It explains to you why you'd have certain, why certain memory things are bad, why minimizing allocations is good and stuff like that. And then, if you haven't heard of Handmade Hero, it's basically a stream where a man makes a game and a game engine in C++ on the stream, and it's an hour long every episode. He's up to 270, I think, days by now. And the Handmade Network is sort of an idea that formed around that, which is that software is slow, and how do you write fast software without having to go afterwards and profile it and stuff. And this has spawned a lot of separate projects. But the basic idea behind this is, and sort of what outlines, it goes in line with the first part of my talk, is that writing fast code isn't like writing comments. It's not something you do afterwards to make people happy. It's something that you have to think about all the time. And if you just take into account that you can write code that works well on a computer, you can write really good code really fast, and you won't have to afterwards go and profile it and fix it. And that's my talk.